Hello, my name is Michael Schuken, and in this video I'm going to cover Computer Science 201 Lab number 8 that has two parts. First being Introduction to PC SPIM, and second one is Arithmetic Operations and Debugging in PC SPIM. So let's start. First of all, to work with MIPS assembly language, we need to download a software called PC SPIM, which is the emulator for an entire MIPS architecture computer with elements like RAM, CPU, compiler, also known as assembler, and basic console for input and output. So here is a link that you can use, and if you click it, it will bring you to the downloads page for PC SPIM and similar programs. Please note that in our labs we assume that you have a Windows operating system machine with PC SPIM version 9.1.9 installed. If you need to work remotely under a different operating system, check out installers at that SourceForge page for Qt SPIM for Linux distributives and Mac operating system. After you get that package downloaded, the installation is pretty straightforward. I already have it installed, so let's proceed. Recall that MIPS architecture has 32 general purpose registers listed in this table here. We will refer to this register file as we make steps to write our first assembly program. Note also that there exist 16 floating point registers called F0 through F15 that can store float type numbers. We will not cover those in this tutorial, but it's handy to know they exist. So let's take a look on how could we create our first assembly language program. To do that, we need to use a text editor such as Notepad in Microsoft Windows. Alternatively, you can opt in to have what's called Notepad++. That is the software that I would be referring to when I edit assembly programs. So here's an example on how the interface looks like. In regular Windows Notepad, there are no lines of code. They're not numbered. So in our case, I will be using Notepad++ to facilitate the delivery of this material. So once you get Notepad++ or just decide to use the regular Notepad, you must keep in mind that PC SPIM is going to work with files that have the .s extension. So when you are creating a text file, make sure to change the extension of it to .s from .txt. So as of now, let's assume that we are going to take this base hello world program and we will put that in a file called hello.s by using the Notepad program. So this file contains the source code of a program to print out a character string hello world. We will later on use PC SPIM to open and execute this program so that you can see what is the output of this program. So I will copy this chunk of code, and here I have already prepared a PC SPIM shortcut. So what I'm going to do is I am going to create a text document. I'm going to call it hello dot s. So that's where I change the extension. And when it's going to ask, would you like to change an extension? I go for yes. Then, if you highlight this in the type field, it's going to say assembly file. So as of right now, that is the empty assembly file. If I right click on this and if I say edit with Notepad, that's what you will have if you are using Notepad++. If you're using regular Notepad, you will just say something like open. I will open that with Notepad++. So at this point, this file is empty. We need to make sure that we do Control V to paste the code that we just had from the lab page. And then I'm going to also do Control S for saving, or I can just go ahead and hit the save button there. So as of now, I am going to minimize this window. So what I can do is I can double click on this assembly file, and if I do this, if you had PC-SPIM installed, then by default your .s files are going to be opened in PC-SPIM. So as of right now, we see that here is the interface of our emulator. The way how it works is that there are several fields here, okay? Most notably, we have the general registers here. So that table that we had in the beginning for register file is just right in front of us here. So here, if we scroll down on that particular field, we see that these are the hexadecimal values of what is stored in those registers in our virtual machine at this particular point. So this middle part here is where I have my instruction memory. So as you can see here, the way how this notation works is that we have a hexadecimal value in square brackets, and that's where the address goes. So basically that is the hexadecimal address in the random access memory that is again emulated for us by PC-SPIM. That will be the first address of an instruction of our program. And then you can see the actual value, the actual hexadecimal value of the 32 bits that represent our actual instruction that's there. So you can see that after that there is the actual assembly line here, though note that here if we have some pseudo instructions like load address from our source code that is displayed right after, some of the lines they will not have a comment from our actual code because those instructions are pseudo instructions and they need to have 2 lines. So for example, the load address command here, where we put a string address into A0, we have 2 instructions here. So that's why sometimes if you scroll here, you can see gaps in here. And it's handy to have this area because here we can see the line number there. So in case we had a syntax error or any problem with our code, we would know that it happened at that position, at that line in our text file. After that, we have the data section. So at this point, we don't have a lot of data there, but if you consider for a moment the source code of our program, we had here, we had declared hello world string. So if I go back to PC-SPIM, this is how that hello world string is going to be represented. So again, keeping in mind that we don't really have types in MIPS assembly, we would still use some designation on how would we like to represent this particular string. So in this case, what we are saying is we have a special directive that says store that string as several ASCII encoded characters. So we are using, by default, we assume that we use American Standard Code for Information Interchange here when we refer to strings. And that is how they look like when they are loaded into our emulated machine. So, and lastly, the window that you have here is for feedback from the program. So basically it's just like a status bar. It tells us what is going on, what is the version of our emulator. If you scroll up, that's the version, so 9.1.9. and then the most important part here is to see that our program has been successfully loaded. That is what we look for each time we open up PC-SPIM with a file. If you ever wanted to reload a program back into PC-SPIM, or clear or reinitialize that if you're opening several programs, what you can do is that you can do File, Open, and then you can select your .s files from the folders. So if you do that, PC-SPIM is going to ask you, would you like to clear the program and reinitialize our simulation? You would say yes, and then whatever the values were here in the general registers, you are going to have them cleared if you want to run that program again. Now, speaking of running that program, to do that, you should go to the Simulator tab, and you now have two options, right? So you can either hit Go from Simulator tab, or you can use a hotkey of F5 to do the job. So if I click that, or if I click F5, I will be presented with this window that says Run Parameters. The starting address there is by default going to be that value, so you should not make any changes to that. That's just how it works. You would hit OK, and then PC-SPIM brings up our input and output console. So here at this point, that's what that program does. It just outputs hello world. Okay, so let's get back and see and analyze how that program works. So the MIPS assembly language program is usually held in a file like the one that we just created with .s extension, and in hello.s we had some of the lines that PC-SPIM processes one by one to determine how to work with our program. So in this particular file, the syntax that we have used is the following. So a sharp sign is used to begin inline comments. Everything from that sharp sign to the end of the line is ignored by our compiler, by the assembler that is built into the PC-SPIM software. So just like comments in any other programming language, you could have your code commented here. Then we have identifiers as a sequence of alphanumeric characters, underbars, underscores, and dots that does not begin with a number. Then we have labels. So a label is declared by putting identifiers at the beginning of a line followed by a column. For example, if you do something like this, if you say str and then use a colon, that will be treated as a label. A label is basically a location somewhere in our program to where we can make references. It's kind of like a bookmark, really. And when this program gets loaded into the RAM, that label gets converted to a particular hexadecimal address, as we have seen that in PC SPIM. So basically, if we have that pointer in the data, it'll be somewhere here. If it was to be a pointer to somewhere where we have a code, that will be in the instruction part. So then we have operation fields that contain something for a machine to do, a machine instruction or a directive for our assembler, for the compiler that will be using our text file to tell the machine what to do. So one or more operands are usually required by all machine instructions. Assembler directives may sometimes require operands, sometimes not. And then we have constants such as strings or row values that we will not change throughout the operation of our assembly program. So for example, in this hello world program, we had this string declared. So str is a label, then ASCII Z is a directive for our compiler to store this value that we have in quotes. That's how we would declare a string value. So basically here, ASCII Z directive will tell the compiler to start storing that raw value in quotes as a string, and a string that is ASCII encoded with a 0 character at the end. That's what ASCII Z stands for. So you can find similar references here. .text and .global and .data are all assembler directives. So they have different meaning in terms of .text and .data designate where we have text segments. So basically, it's our instructions that are stored here, and then we have the .data segment where we have constants or maybe some memory allocated for our operation. So here, .text is a directive that tells the assembler to place what follows after in the text segment. So basically, .text tells PC SPIM to start filling this section here, right? That's where our actual code went. .data will do the same thing, but to fill this section. And then we have these two lines that are really important for any program that you will ever write for PC SPIM. We have these two lines. So we have a .global directive, and then we have a special identifier, _start. So these two lines attach the label _start to the first instruction, so that when the assembler starts working on this program, it knows where to begin executing our code. So all exercises in our labs will have these two lines there unchanged. Okay, so at this point we went through the very basics of working with PC SPIM and loading our code. So I'm going to skip some of these instructions here. And then we would go to some more material about the possible operations that we can do with our console. So console is an interesting component of MIPS emulator in this case, because there we can do both input and output. So technically it is like a small simulation for a screen and a place where we can work with keyboard input. And accordingly, we have here a table that tells us how could we do output, and that means print to console window, and how we can read a value from the user so that we can type something into the console. So we will have to tell the program to wait until we provide that with our peripheral device, the keyboard. And then there are some interesting special cases where we need to do a system call, where we need to allocate more memory or terminate the program. So in all of those cases, you would have this call code that is going to be immediate value. That means just literal immediate value of 1 through 10, and that should be loaded in V0 before we can use a system call instruction. So, in the arguments column, you can see that first of all we hint you on what are the parameters that need to be provided for that particular service, so that when you do a system call, it can be executed correctly. So sometimes results section will contain more information on where the output of that particular system call goes. But in case for printing out, the actual result is going to be a printout in the console. So if we are printing integer value, here is an example code how we can do this. So li means load immediate value of, say, 89 into register A0. It's nice to have a reference of why we're using A0. A0, as you can see from this table, just like other A registers, is used to pass arguments to functions. So that tells you that system call is one type of those functions. So system calls will rely on one of these registers when you are working with system calls. So, getting back to this example code, if you are working here with load immediate instruction, number 89 will be loaded into register A0. After that, we load call code with the same command, load immediate value of 1, that will represent our call code for print integer. We will load that in register V0. So again, if we go back, V0 is here, and that's something that is used for expression evaluation in different cases and results of a function. But in this case, because we're doing a system call, register V0 is going to be used in a little bit of an extraordinary way. So V0 will not be a parameter for printing integer, but it will be something that will determine what is the service. So if you are loading integer 1 into V0, that will stand for print integer. And after you have loaded the call code into V0 and arguments into registers A0 through A3, you can then do a system call. Okay? So you can later on discover different example codes here, and as you can see, in cases where we need to read a value from the user, we might not need parameters at all, because in this case, if we are, say, reading an integer from the user, we only need to load call code of 5 into v0 and then do a system call. Now, in the results section, after that system call is performed, your console window will be expecting you to type in a value and hit enter. Only after user does that, you will have that number assumed in v0. So again, here is where v0 gets used both as a register for input and for output. And here is a perfect example of terminating the program successfully. So stopping the program only takes the actual call code and system call. So system call code of 10 means stop the program and unload that from the RAM. So we did talk a little bit about strings in PC SPIM, so keep in mind that you can include these special characters in your strings so that you can make more sophisticated printout when you are showing strings to the user. If you use \n, that is new line. If you want tabulation, that's \t. And if you need to use double quotes as something that is not part of the code but gets printed to the console, there is the \double quote. Now, to discover more options for writing your code, I advise you to take a look at the MIPS reference card that we have here. Ask your instructor on providing you more information about how to read and understand this reference card, but basically this card will have most available instructions here explained, as well as system calls and exception codes and assembler directives and more. So for this part of the lab, let's go into the lab assignment. To complete this lab, here's a task for you. What you need to do after you try the lab and read the notes, try to do an assembly language program that's called Peter.s, and try to make that program do the following. Prompt your user to enter his or her name. So the prompt will be like, hello, what is your name? Then the user will be expected to enter the name. For example, you can test it with the name Peter. Then the program will prompt the user again by asking, how old are you? The user will then supposed to be entering any integer, for example, age of 20. After that, the program should print out the answer in this way. Peter is 20 years old. Note that that will require you to use the new line character at the end to keep your output tidy and user-friendly. So to complete this lab, you will need to provide a source code in the file peter.s and make some screenshots of PC SPIM having your program successfully loaded and having the right console output. So if you do that program right, after you run it, you should acquire that output here in the console. So that will conclude the first part of our lab number 8.